This is an FPGA-based spiking neural network that controls a car. The important part is that it learns live, on chip, in real time. No offline training, no external computation. Everything runs on the FPGA itself. Let's walk through how it works, starting from the individual building blocks. We start with the input side. A light-dependent resistor is set up as a simple voltage divider. When light falls on the LDR, the output voltage increases. More light, higher voltage. This analog voltage is fed into an analog to digital converter, which produces a 10-bit digital value. That digital value is serialized and sent to the FPGA. Inside the FPGA, we have a Verilog-based model of a leaky integrate and fire neuron. The neuron's behavior is simple. The higher the digital input value, the more frequently it fires spikes. A low input means fewer spikes. A high input means rapid firing. Next, the synapse. Inside the FPGA, we also have a digital model of a memristor. A memristor acts as a programmable conductance. Its resistance changes depending on the electrical signals it receives. Instead of sweeping a full IV curve, we send spikes directly. When positive spikes are applied, the conductance increases. When negative spikes are applied, the conductance decreases and resistance goes up. This gives us the characteristic V-shaped curve, conductance plotted against the number of spikes. This is how we've characterized our memristor model independently. The SNN uses two separate memristor crossbar arrays connected by a pool of hidden neurons. Let's walk through the signal path from sensor to motor. At the top, we have 4 input LIF neurons, one for each sensor direction. When a sensor detects light, its neuron fires spikes. Each neuron maps to one row of the first crossbar. When input K spikes, that spike broadcasts across the entire row, hitting every column through a different conductance value. This is the first crossbar, G in, a 4x28 matrix. Every purple dot is a memristor, a programmable conductance. The column current for hidden neuron J is the sum of each spiking input's conductance in that column. That sum becomes the input current to the hidden neuron. The 28 hidden neurons each receive their column current, integrated over time with a leak term, and fire a spike when their membrane potential crosses threshold. These hidden spikes now become the input to the second crossbar. The second crossbar G is 28 rows by 4 columns. Each hidden neuron spike broadcasts across its row, and each of the 4 output columns sums up the weighted contributions. Same crossbar current sum mechanism, different dimensions. The 4 output neurons, front, left, right, back, fire at rates determined by those column sums. We normalize the firing rates to compute a direction angle, which is sent over Wi-Fi to the car. Let's see the full cycle. First, training. Here is how training works step by step. To teach it a direction, say, front, shine a light toward the front sensor. Press and hold the train button together with the front direction button simultaneously. As long as both buttons are held down, the FPGA runs supervised learning at 100 epochs per second. With every epoch, it increases the crossbar weights feeding into the front output neuron and decreases the weights into the other 3, left, right, and back, using the current spike pattern as the learning signal. When you release the buttons, that training pass is complete. The front direction has been learned for that particular light pattern. Now repeat the process for the remaining directions. For each direction, you can also vary the angle and intensity slightly across a few samples so the network generalizes better. After cycling through all 4 directions with a few samples each, the network is fully trained. The weights in the crossbar are locked, no more learning. From this point, the system runs inference continuously. Light hits the sensors. The input neurons fire proportionally. Those spikes propagate through the crossbar into the hidden layer, and the hidden layer activates the 4 output neurons. The FPGA compares the firing rates of all 4 output neurons, normalizes them, and determines an overall direction. That direction command is sent over Wi-Fi to an ESP32 mounted on the car. Now that training is done, let us test it out. As I shine the light in the front, the front output neuron fires. Similarly, for each of the direction that we have trained, it fires accordingly. When we give a corner input between two known outputs, say front and right, they fire at similar rates, from which we get an output angle accordingly. These directions are ultimately sent over Wi-Fi to the car.